An astronaut on Mars would absorb enough radiation in 6 months to exceed NASA's current lifetime exposure limit, and that is before accounting for the journey to get there. This is the most underreported challenge in human Mars exploration, and the data that quantifies it came from an instrument riding on the Curiosity rover that has been measuring radiation on the Martian surface every day since 2012. The instrument is called the Radiation Assessment Detector, or RAD. It was built by Southwest Research Institute and has been operating continuously on Mars since Curiosity landed in Gale Crater on August 6, 2012. RAD measures 2 categories of radiation: galactic cosmic rays, which are high-energy particles arriving continuously from outside the solar system, and solar energetic particles, which are bursts of charged particles released by solar flares and coronal mass ejections. Both are dangerous to human biology, for different reasons and in different ways. On Earth, 2 natural systems protect us. First, Earth's magnetic field deflects charged particles, preventing most galactic cosmic rays and solar energetic particles from reaching the surface. Second, Earth's atmosphere, with a surface pressure of about 101 kilopascals, provides significant mass shielding that absorbs and scatters radiation before it reaches ground level. Mars has neither system operating effectively. Mars lost its global magnetic field billions of years ago when its core cooled and the internal dynamo shut down. It retains only patchy localized remnant magnetism in parts of the crust, which provides no meaningful protection against incoming radiation. Mars's atmosphere has a surface pressure of roughly 600 to 700 pascals, less than 1% of Earth's. That thin atmosphere provides some shielding, but is orders of magnitude less effective than Earth's. The RAD data, published in a landmark 2013 paper in Science by Don Hassler and colleagues, measured a surface radiation dose rate of approximately 0.64 millisieverts per day on Mars. For context, the annual radiation exposure limit for radiation workers in the United States is 50 millisieverts. The average annual background dose for a person living at sea level on Earth is about 3 millisieverts. At the Martian surface rate, an astronaut would accumulate approximately 233 millisieverts in a year of surface operations. NASA's current career limit for astronauts, which has been revised upward in recent years, is now set at 600 millisieverts lifetime. A Mars mission involving 6 months of transit each way and 18 months on the surface would deliver roughly 1,000 millisieverts from surface exposure alone, not including the transit. During transit, with no planetary atmosphere or magnetic field offering any shielding, the dose rate is even higher than on the surface. The 2013 paper also reported the transit dose measured by RAD on Curiosity's journey to Mars, approximately 0.66 millisieverts per day during cruise, totaling about 300 millisieverts for the roughly 253-day journey. The total estimated radiation dose for a round-trip Mars mission is approximately 1,000 millisieverts or more. That is a significant cancer risk elevation. Studies of radiation-exposed populations suggest that 1,000 millisieverts increases lifetime fatal cancer risk by roughly 3 to 5% above the baseline, depending on the individual's age and sex. That is not instantly lethal, but it exceeds acceptable occupational risk standards under current frameworks. Solar energetic particle events add an acute risk layer. A large solar flare can deliver a dangerous dose in hours. On Earth or the ISS, astronauts can shelter. On Mars, a storm shelter with additional shielding, possibly constructed from water, polyethylene, or Martian regolith, is an engineering requirement, not an option. Solutions being researched include hydrogen-rich shielding materials, which are more effective at stopping cosmic rays than metal, subsurface, or partially buried habitats, and pharmaceutical countermeasures, including drugs that reduce radiation sensitivity or accelerate DNA repair. None of these fully solve the problem yet. The radiation environment on Mars is not a reason to abandon human exploration. It is a specific, quantified engineering problem with a clear data foundation from RAD, and solving it is one of the primary technical requirements any human Mars architecture must meet. Follow for more on the real science behind human Mars missions, and tell me, knowing that a round-trip Mars mission exceeds current lifetime radiation limits, Would that change your decision to go if you were given the choice?